Imagine this. You're commuting to work, coffee in hand, your Stanley travel mug, the one everyone seems to have. You give the lid one final twist to make sure it's sealed tight, and then it detaches completely. Hot liquid sprays across your hand, across your lap, across your car seat. You are now one of 38 people. In December 2024, the US Consumer Product Safety Commission, the CPSC, issued a recall on 2.6 million Stanley Switchback and Trigger Action stainless steel travel mugs. 38 people had been burned worldwide. 11 required medical attention. And the cause? Buried in four words in the official recall notice. Lid threads can shrink. A plastic thread on a $45 travel mug designed to hold boiling liquid failed because it shrank. Today, we're going to find out exactly how. To understand the failure, we first need to understand the product. Stanley has been around since 1913. For most of that century, it was an industrial brand. Heavy-duty vacuum bottles for construction workers, oil rig crews, and hikers. Then, around 2020, TikTok happened. The Stanley Quencher tumbler became a cultural phenomenon. Sold out in minutes, resold on eBay for triple the price, and alongside it, the Switchback and Trigger Action travel mugs, the specific products at the center of this recall. Here's what they are: a stainless steel double walled vacuum body that keeps your drink hot for hours, a polypropylene lid with a push button trigger mechanism. Press the button, the spout opens. Twist to close. Available in 12, 16, and 20-ounce sizes. Sold at Amazon, Target, Walmart, and Dick's Sporting Goods for between $20 and $50. On the surface, a premium product, excellent insulation, a trusted brand with over a century of history, a lid that locks shut. But inside that lid is where the engineering story starts to fall apart. The Consumer Product Safety Commission received 91 reports worldwide of the same failure: the polypropylene lid detaching from the mug, not slowly, not gradually, suddenly, during normal use. Hot coffee, hot tea, soup, whatever was inside poured out instantly. 38 burned injuries, 2 in the United States. 11 people required medical attention worldwide. Now read the specific language from the official recall notice. It says, and this is the exact wording, the mug's lid threads can shrink when exposed to heat and torque, causing the lid to detach during use. Heat and torque. This mug is designed to hold hot liquids. The lid is designed to be twisted closed. It failed because of heat and because of twisting. That is not a user error. That is not bad luck. That is a specific, identifiable engineering failure with a specific cause that we can trace molecule by molecule to exactly what went wrong. Let's start with the material. There are two materials at the center of this failure, and they behave very differently when temperature changes. Material number one, stainless steel. That's the mug body. It's a metal alloy, iron, chromium, nickel, and it's one of the most dimensionally stable materials in engineering. Heat it, it expands a tiny amount. Cool it, it contracts a tiny amount. Predictably, reliably, the same way every single time. Material number two, polypropylene, abbreviated PP. That's the plastic used in the lid and critically in the threads that screw the lid onto the mug neck. Polypropylene is a thermoplastic. Heat it, it gets softer and expands. Cool it, it gets harder and contracts. But here's the critical number. Polypropylene expands and contracts at a rate up to 8 times greater than stainless steel. Engineers measure this property with something called the coefficient of thermal expansion, or CTE. Think of CTE as a material sensitivity score to temperature change. Stainless steel, about 17 units. Polypropylene, between 100 and 180 units. 8 times more sensitive. Here's how to picture it. Imagine two people trying to fit through the same doorway. One person barely changes size no matter the weather. The other expands dramatically in summer heat and shrinks significantly on a cold winter morning. If the doorway was designed for a perfect fit on a mild spring day, it'll be too tight on a hot day and too loose when it gets cold. That doorway is the thread fit between the Stanley lid and the mug, and it was designed with very little room for temperature-driven change. Now let's talk about threads. The Stanley lid screws onto the top of the mug exactly like a bottle cap screws onto a water bottle. Inside the lid, there are spiral grooves called female threads. Around the mug neck, there are matching spiral ridges called male threads. When you twist the lid, these grooves interlock and the lid locks in place. For this system to work, the threads have to fit together precisely. Engineers designed this fit using something called dimensional tolerance, a tiny, carefully calculated gap between the mug neck threads and the lid threads. small enough that the lid stays locked under the weight of liquid and the force of being opened and closed every day, but large enough that you can actually turn the lid. Here is the critical requirement. That gap, that dimensional tolerance, has to remain correct throughout the entire working life of the product. If the gap gets too large, the threads barely interlock. The lid becomes loose, and loose threads under pressure from hot liquid inside eventually detach. Every time you fill this mug with hot coffee, the polypropylene lid warms up. Every time it cools down, the PP threads contract, shrinking slightly more than the stainless steel threads below them. Every dishwasher cycle at 140 degrees repeats the process, each cycle a tiny dimensional change. After dozens, then hundreds of cycles, the thread engagement depth has shifted from engineered tight to critically loose. There's a third phenomenon at work that makes this failure mode even more insidious. It's called stress relaxation in polymers, or more commonly, creep. Here's what it means at a 10th grade level. When you screw a plastic lid onto a metal mug and tighten it, you're stretching and compressing the plastic threads. Those threads are under mechanical stress. In a metal part, that stress just stays there. The metal holds its shape rigidly, but polypropylene is different. Under sustained stress, the polymer chains, the long molecular structures that make up the plastic, slowly rearrange themselves to relieve that stress. Over hours, days, and weeks of use, the plastic threads very slowly deform at the molecular level until the stress is gone. The thread doesn't snap, it doesn't crack, it creeps very slowly, invisibly, into a slightly looser shape. Now combine creep with heat cycling. The PP threads shrink a tiny bit more each time they cool from hot to room temperature. The thread engagement, how deeply the threads interlock, gets shallower and shallower with every use. The mug that failed on day 200 was weakening since day 1. This is why the failure appeared across millions of units after months of use, not in the first week. The threads passed every factory test. Here's the uncomfortable truth. Stanley almost certainly tested this product before shipping 2.6 million units, and it probably passed every test. Brand new mugs with tight, fresh threads, tested in a controlled lab environment, hold perfectly fine. The dimensional tolerance is correct. The threads engage deeply. The lid doesn't move. The failure emerges at the 100th dishwasher cycle, the 200th fill, the mug that has lived through a full year of daily use, traveling in a car, getting dropped, being washed at high temperature, refilled with boiling liquid, and carried by a handle that applies torque to the lid every single time it's picked up. This is called long cycle fatigue failure. The product performs perfectly on day 1. It degrades invisibly through normal use, and then it fails at a point that standard short cycle testing never reached. There's also a design-specific problem. The switchback and trigger action lids both use a push-button mechanism. Every time you push that button to open the spout, you apply a small lateral sideways force to the lid. That lateral force adds torque stress to the already degraded threads. It's the final push that converts loose lid into detached lid. Not one failure mode. 3. Working together. Material mismatch, cumulative thermal shrinkage, and mechanical side loading from the trigger, all invisible until they combine. So how should this have been designed to prevent exactly this failure? Let's think like engineers. Fix number 1, choose a better material for the threads. Fiber reinforced polypropylene, where tiny glass or nylon fibers are embedded throughout the plastic, has a dramatically lower CTE than pure PP. It resists thermal contraction and resists creep far better. Cost difference? A few cents per unit at manufacturing scale. Fix number 2, design deeper threads. Thread depth determines how much engagement surface exists between the lid and the mug. Deeper threads mean more material has to fail before the lid can detach. They're more forgiving of small dimensional changes from heat cycling. Fix number 3, add a secondary locking feature. Many pharmaceutical closures and industrial caps include a ratchet, snap lock, or quarter-turn bayonet mechanism that physically prevents rotation unless you actively release it. This creates a mechanical barrier between loose lid and flying lid. Fix number 4, test the product for its full use lifetime before shipping it. 1,000 fill and dishwasher cycles, not 10. If the lid degrades after 200 uses, a 1,000 cycle test finds it before consumers do. None of these are exotic solutions. All of them exist and are used in other industries today. This is exactly what failure mode analysis exists to prevent. If you own a Stanley Switchback or trigger action stainless steel travel mug, step 1. Check the bottom of your mug. The recall covers specific product identification numbers. The full list is available at c.gov and at stanley1913.com. If your number is on that list, you have a recalled product. Step 2, stop using it immediately, not after you finish the coffee in it. Now. Step 3, contact Stanley. They will provide a free replacement lid with the updated corrected design. No charge, no return needed for the mug body. And here is a tip that applies to every travel mug you will ever own, recalled or not. Do not over tighten a plastic threaded lid. The most common user habit is to crank the lid as tight as possible, assuming tighter means safer. But over tightening maximizes the stress on the plastic threads from day one, which accelerates exactly the kind of molecular creep we described. Firm is the right setting, tight is counterproductive. If the liquid leaks when you apply firm pressure, the thread engagement is already compromised, and that's the mug telling you something is wrong. The Stanley recall is not a story about a bad company. Stanley has been making reliable products for over a century, and they issued the recall and provided free replacements promptly. This is a story about a specific teachable engineering failure. Material mismatch. Polypropylene threads on a stainless steel mug with coefficients of thermal expansion 8 times apart. A cumulative thermal shrinkage problem that no short cycle lab test was designed to catch. A push button trigger mechanism that added exactly the wrong kind of force to already weakened threads. 3 failure modes. All invisible individually, all catastrophic in combination. 38 people got burned because of a few microns of dimensional change in a plastic thread. And behind those few microns is a lesson that every product engineer needs to hear. Design and test for the entire life of your product, not the first day, the 500th day. The next time you pick up a travel mug or a water bottle or a pill container or any product with a threaded plastic lid, you now understand what's working inside those threads, the engineering holding your hot liquid in place, and what has to go wrong for it to stop working. That's what why products fail is for. Until next time.